1992. The Quincy Mine in Michigan. Engineer James Corrigan goes down into the engine room to document the equipment before shutdown. He stops beside the Nordberg hoisting engine. It is running. The drum turns. The rope is tight. Grease runs through the same channels it did 60 years earlier. This machine was installed in 1929. It hauled more than 8 million tons of copper ore to the surface. It was never taken offline for a full, major rebuild. Corrigan writes in his notebook, original brake shoes, original main rope, wear within allowable limits, 63 years of continuous service. Today, the average service life of a steel hoist rope on a modern hoist is 3 to 5 years. Brake shoes are changed every year. Some are changed twice a year. So what did engineers in the 30s know that we do not? This story is not nostalgia for the past. It is an engineering investigation. In the 1920s and 1930s, the United States lived through a golden era of mining. Copper from Michigan, iron from Minnesota, coal from Pennsylvania and West Virginia. Mine hoists were the heart of that industry. They lifted ore from depths of hundreds of meters. They lowered miners to their shift and brought them back alive. These machines worked 24 hours a day, 365 days a year. A shutdown cost money. A shutdown cost lives. So they did not stop. The hoist at the Calumet and Hecla mine, installed in 1918, ran until 1968, 50 years, without replacement of its major core components. The hoist at the Minnesota mine, commissioned in 1926, was dismantled in 1984. 58 years. Original bearings. Today, mining companies plan annual replacement of critical parts into the budget. Ropes, brakes, drum linings, bearings. Why? The answer is not one single factor. It sits at the crossroads of design philosophy, metallurgy, economics, and human psychology. We begin with how hoists were built in an era when the word reliability meant something stricter, something heavier. We will move through the Nordberg Works in Milwaukee, through the copper country mines in Michigan, through metallurgical laboratories and economists' offices. And we will watch slowly, step by step, how something important was lost. This is a story about engineers who built for decades, and about a world that decided decades were too long. Chapter 1. The machine that outlived its makers, Milwaukee, Wisconsin. Winter, 1927. At the Nordberg Manufacturing Company, engineer Bruno Nordberg Jr. leans over his drawings. He is 34 years old. He is the son of the company's founder, Bruno Nordberg Sr., a Swedish immigrant. On the table is a hoisting engine project for the Quincy Mine, a $2 million order. In 1927 money, that is the cost of a small factory. Nordberg Jr. draws a circle in red pencil around a number, 1.5, the safety factor for the main shaft. He crosses it out. He writes 4.0. Chief Engineer Henry Schultz steps to the table. This will raise the price by $40,000, he says. I know, Nordberg answers, but I do not want this machine to break in my lifetime. It did not break in the lifetime of his grandchildren either. The Nordberg hoist for the Quincy Mine entered service in 1929. A drum 4.5 meters in diameter. Motor power, 2,000 horsepower. Hoisting depth, almost 2 kilometers. The machine weighed more than 300 tons. Every major part was calculated with a safety factor from 3 to 5. That meant a part designed for a 10-ton load could, in real life, take 30 to 50 tons before failure. Today, the standard safety factor for similar structures is closer to 1.5 to 2. The difference looks small on paper. In practice, it means everything. When a shaft works at half of its limit, metal fatigue grows slowly. Micro cracks take decades to appear. When a shaft works at 80% of its limit, fatigue grows fast. Micro cracks show up in years. Nordberg understood that. Not through computer simulation, there was none. Through the hard memory of machines and accidents. His father, Bruno Sr., arrived in America in 1879. He worked around the mines of Michigan. He watched cheap machines fail. He watched people die. When Bruno Sr. founded Nordberg Manufacturing in 1886, he set a rule the company kept for 50 years. We build machines that outlive us. And they did. The Quincy mine hoist ran until 1992. 63 years. It lifted copper ore worth more than $2 billion in modern prices. That $40,000 Nordberg Jr. spent on a thicker, stronger shaft paid back not once, but thousands of times. But it was a different economy, a different mindset. Today, that mindset is often mocked with one word: over-engineering. People say it like an accusation. In the 30s, they called it common sense. Depth, 900 meters. Darkness, humidity, 90%. Temperature, plus 30 degrees Celsius. The hoist cage sinks slowly into the Anaconda copper mine in Butte, Montana. On board, 24 miners. The night shift. Above them hangs 1,200 meters of steel rope, 18 tons of metal holding their lives. The year is 1931. That rope was made at the Roebling plant in Trenton, New Jersey, the same works that supplied rope for the Brooklyn Bridge. The company's founder, John Roebling, died in 1869 from tetanus after an injury during the bridge project. But his principles lived on for generations. The rope for Anaconda was made to an extra-improved plow steel specification, the top grade of its time. Tensile strength, 170 kilograms per square millimeter. Today, that number would be considered average. But the secret is not the raw strength. The secret is how the rope was made. Every wire in that rope came from repeated drawing through calibrated dies. 7 passes. Each pass, temperature control. Each pass, diameter checked with precision down to 1/100th of a millimeter. The process took 3 times longer than standard production, but it produced wire without internal defects, without microvoids, without tiny weak points where stress concentrates and cracks begin. That kind of wire did not fail like a trap door. It gave warnings, it stretched, it changed shape, it spoke before it snapped. Anaconda's chief engineer, William McDonald, inspected the rope himself every week. He looked for bird caging and loose wires, the early signs of fatigue. He measured diameter, because shrinkage meant wear, and wear meant danger. After 15 years of service, the main Anaconda hoist rope showed less than 3% wear. They did not replace it because it was worn out. They replaced it because the company chose to increase the payload. They cut the old rope into samples. Lab tests showed it could have worked for 20 more years. Today, rope production is built around speed, automated lines, minimal time per operation. Modern ropes can be stronger. Their tensile strength can reach 200 kilograms per square millimeter and higher. Yet they often fatigue sooner. In 2018, Bryden Bakert, one of the world's largest mine rope producers, published research. Average rope life in deep mines, 3 to 5 years. Compare that to the 30s. Ropes often lasted 15 to 25 years. So what changed? Metallurgy improved. Steel became cleaner on paper, but quality control changed its character. It became statistical. Instead of checking every meter, you check samples. That saves time. It saves money, and it costs years of service life. Imagine a drum that weighs 50 tons. It spins at 40 revolutions per minute. A rope is wrapped around it, holding a cage with 20 people inside. Now imagine you have to stop that drum in 3 seconds. Mine hoist brakes are not car brakes. They are machines the size of a small house. At the Empire Mine in California, which operated from 1851 to 1956, the braking system weighed 12 tons. It had 2 main components. First, the brake drum, a steel ring 3 meters in diameter, 150 millimeters thick, perfectly round, out of round tolerance, no more than half a millimeter. Second, the brake shoes, wooden blocks soaked in a special compound, not rubber, not metal. Wood. Why wood? Engineer Charles Wyman, who designed braking systems for hoists in the early 20th century, wrote in his 1912 manual, "Wood forgives the operator's mistakes. Metal does not. A wooden shoe, when overheated, chars slowly. It smokes. It warns you. A metal shoe, when overheated, can lose friction suddenly. This is called fading. The brakes do not weaken. They can simply stop biting." At the Empire Mine, they used hickory, one of the toughest American woods. The shoes were made by hand. Each one was fitted to its drum individually. The process took a week, but those shoes lasted 10 to 15 years. The secret was not only the material, the secret was the entire system. The brake levers at the Empire Mine had a mechanical advantage of 1 to 12. That meant the operator's force was multiplied 12 times. The operator did not strain. He moved smoothly. No jerks, no shock loads, no violent on-off braking. Every stop was controlled. Every stop spread, wear evenly. Today, braking systems are electro-hydraulic. They are faster, they are stronger, they are computer-controlled. But they also create sharp peak loads, loads the old wooden systems rarely produced. Modern composite brake pads can handle temperatures up to 500 degrees. They are stronger than wood, yet they often need replacement every 6 to 12 months. At the Empire Mine, the same shoes went through tens of thousands of braking cycles. On many modern hoists, pads are counted in thousands. The difference is not better versus worse. The difference is philosophy. The 30s, build it so it does not break. Today, build it so it is easy to replace. Copper Queen Mine, Bisbee, Arizona, 1934. A hoist operator named Frank Morales clocks in for the 6 a.m. shift. He has worked this machine for 11 years. He knows it better than he knows his own wife. Morales sits at the levers. He listens. The main motor hums at a pitch he can identify without instruments. The vibration through the seat tells him about the bearings. The smell of the oil tells him about gearbox temperature. Today he notices something new. A faint knock, barely audible. Once every 3 drum revolutions. Morales stops the machine. He spends an hour inspecting. He finds it. 1 bolt at the rope drum. Coupling has backed off by a quarter turn. He tightens it. The machine runs perfectly again. If he had missed it, that bolt could have walked out within a month. The drum could have shifted. The rope could have climbed off its track. People could have died. This is not an exception. This is the system. On American mines in the 30s, the hoist operator was not just a person pulling levers. He was a diagnostician. He was a mechanic. He was part of the machine. Operator training took 3 to 5 years. Year 1, helper. Cleaning, lubrication, watching, learning the feel of the equipment. Year 2, trainee. Operating under the eyes of an experienced operator. Year 3, solo work on auxiliary hoists. Years 4 and 5, qualification exams for the main hoist. The operator knew the machine because he grew up with it. He knew its sounds. He knew its rhythms. He knew how it behaved in cold and in heat, in dry air and in rain. And he knew when something was off, before alarms existed, before sensors did the thinking for him. At the Homestake mine in South Dakota, the deepest gold mine in North America, there was an operator named Olaf Peterson. He worked the main hoist for 32 years, from 1926 to 1958. Peterson kept a diary, every day, notes about the machine's condition, oil temperature, vibration at different speeds, brake behavior. That diary is kept in the Homestake Mine Museum archive, 123 notebooks. When the company's engineers studied Peterson's notes after he retired, they discovered something unsettling and impressive. He had predicted every serious fault weeks, sometimes months, before it became critical. Not once in those 32 years did the main hoist suffer an emergency shutdown. Peterson did not have an engineering degree. He finished 8 grades of school, but he knew his machine. Today, hoist operators often receive training that lasts from 6 weeks to 3 months. They work rotating shifts. One operator might run 3 different hoists in a single week. They do not learn the personality of each machine. They learn protocols. This is not a criticism of people. It is a criticism of the system. When a machine is someone else's, you notice only obvious problems. When a machine is yours, you feel the smallest change, and that difference becomes years of service life. Pittsburgh, Pennsylvania, 1928. The Jones and Laughlin Steelworks. A metallurgical engineer named Harold Weber watches a steel pour. Molten metal, around 1,600 degrees, flows from the converter into a mold. Weber holds a stopwatch. He times the pour, 8 minutes, exactly as specified. Then he times the cooling schedule, 12 hours to the first stage, another 24 to the second. Steel that solidifies too fast carries internal stress. It becomes brittle. It cracks. Steel that solidifies correctly develops an even structure. It stays springy instead of fragile. It lasts for decades. Jones and Laughlin supplied steel for mine hoists across America. Their specification demanded slow cooling, at least 36 hours for large castings. That took space. That cost money. That slowed production. But it produced metal that resisted fatigue. Hoist shafts made from that steel worked 40 to 50 years without signs of fatigue cracking. Today, metallurgy has reached remarkable heights. Alloy steels, heat treatment, controlled cooling, better measurement, better repeatability. But time is money. Modern production is optimized for speed. A casting that used to cool for 36 hours might now cool for 6 to 8 hours in controlled conditions. Does that affect quality? In 2012, the American Iron and Steel Institute published a study on the longevity of large steel products. Its conclusion: the average time to fatigue crack initiation fell by 20 to 30% compared with products from the middle of the 20th century. The authors added a careful note. This does not mean modern steel is worse. It means we optimize other parameters. Which parameters? Cost of production, delivery speed, dimensional accuracy. Longevity is not at the top of the list. This is not a conspiracy. It is economics. A mining company in the 30s planned 50 years ahead. They bought equipment meant to last the life of the mine. A modern mining company often plans 5 to 10 years ahead. They buy equipment meant to last until the next upgrade cycle. Why pay for steel that might live 50 years if, in 10 years, you will replace the machine with a new model anyway? The logic is clean, it is even rational, but it builds a world where nothing is meant to last for long. Some things are so ordinary that people stop seeing them. Lubrication is one of them. But at the Bingham Canyon mine in Utah, the largest open-pit mine in North America, lubrication was treated with something close to reverence. The chief mechanic, Ralph Jensen, had worked there since 1919. He outlasted 4 directors, 2 world wars, and the Great Depression. And he never changed the lubricant supplier, not once. Valvoline delivered a special blend for Bingham Canyon, mineral oil with lead soaps and graphite added. It was not the cheapest. It was not the most fashionable. But it worked. And Jensen cared about one thing only: what worked. The main hoist bearings at Bingham Canyon were lubricated every 8 hours. Exactly, no exceptions. No, we'll do it later. Jensen personally checked viscosity every week. He had a dedicated tool, a Saybolt viscometer, a brass instrument about the size of a thermos. He dipped it into the oil. He timed the flow. He wrote the number down. If viscosity dropped by 5%, the oil was replaced. Not 10%, not 15, 5. Was that paranoia? Or was it science wearing a work shirt? In 1946, the American Society of Mechanical Engineers ran a study on bearing wear in the mining industry. The result was blunt. Mines with strict lubrication regimes saw average bearing lifetimes 3 times longer than mines with standard regimes. 3 times. A bearing expected to last 5 years lasted 15. Jensen never read that study. He retired in 1945. But he understood the principle without a paper in his hands, because he watched the consequences day after day. He watched bearings run cool instead of hot. He watched machines stay quiet instead of getting rough. He watched downtime shrink. Today, lubrication is often automated. Centralized systems feed oil on schedule. Sensors track pressure and temperature. It is efficient. It is consistent. It does not require a person with a viscometer and a notebook. But an automatic system does not sense in the human way. It executes a program. It will not notice that a new batch of lubricant has a slightly different feel. Just enough to change how it clings, how it films, how it carries heat. It will not suspect that the machine room's temperature pattern has shifted and the schedule needs to be adjusted. It will not know that this specific bearing has a microscopic defect and needs more frequent lubrication to survive. A person who truly knows the machine will catch those small signals. Automation will not. That is not an argument against automation. It is an argument for understanding its limits and not pretending those limits do not exist. New York City, Wall Street, 1933. The Great Depression at full force. Inside the offices of the Anaconda Copper Mining Company, the finance director, Cornelius Kelly, studies a capital expenditure report. The company is in trouble. The price of copper has fallen from 18 cents per pound to 5. The stock has collapsed by 90%. Kelly scans the report, looking for places to cut. His eyes stop on one line. Replacement of hoist number 3, $800,000. The hoist is 25 years old. In normal times, it would already be scheduled for replacement. Kelly calls in the chief engineer. How much longer can it last? The engineer pauses. He does not guess. He weighs the machine in his head. If we maintain it properly, another 20 years, maybe 30. Kelly draws a line through the item. That hoist stayed in service for another 28 years. It was replaced in 1961, not because it failed, but because the mine shifted to a new extraction technology. The Great Depression taught American industry to value what it already had. When you cannot buy new, you keep the old alive. Here is the paradox. Some of the most reliable machines were preserved and, in practice, perfected in the hardest times. The 1920s were a boom. Companies had money for almost everything. The 1930s were the crash. Money vanished. And yet, in the 1930s, maintenance discipline became the strictest. They treated every machine like it was the last one they would ever get. In Butte, Montana, one company introduced a zero tolerance for wear policy. Any part showing wear beyond 5% of the allowable limit was replaced immediately. Paradoxically, maintenance spending went up, but emergency repair costs dropped to zero. Total savings over 10 years, more than $1 million. In 1937, the Engineering and Mining Journal published an article titled, "Why It Is Cheaper to Build for Life." The author, engineer Robert Stewart, laid out the math. A hoist that costs $1 million and lasts 50 years costs $20,000 per year. A hoist that costs $600,000 and lasts 15 years costs $40,000 per year. Then add replacement costs, add downtime, add risk. Cheap becomes expensive. Today, that math is rarely done in the real decision room. Why? Because the planning horizon changed. In the 30s, mine owners thought 50 years ahead. Today, investment funds often think 5 years ahead. Quarterly reports, annual returns, the next cycle. A hoist that lasts 50 years is an asset for grandchildren. A hoist that lasts 10 years and then needs replacement is an opportunity. Write off old equipment and announce new capital investment in the next report. Accounting beat engineering. 1926, the Kennecott Mine in Utah. A new director, Stephen Birch, sets a target: increase output by 30%. Chief engineer Harold Timmons arrives with calculations. We can increase hoist speed by 20%. That gets us most of the gain. Do it, Birch says. Timmons shakes his head. I cannot. If we increase speed that much, rope wear will double. Instead of 15 years, we get 7. Birch thinks. Then install a second hoist. $3 million. Then run 3 shifts instead of 2. People will wear down. Accidents will rise. So what do you propose? Timmons proposes a compromise. Increase speed by 10% and increase loading time. The net gain becomes 20%. Rope wear stays within normal limits. It works. This story shows a principle that ruled mining in the 20s and 30s. Speed is the enemy of reliability. Mine hoists of that era ran slowly by modern standards. At Kennecott, hoisting speed was 7 meters per second. Modern deep mine hoists run 15 to 18 meters per second. That is roughly twice as fast. But wear does not grow in a straight line. Doubling speed is not double the stress. It can mean 4 times the braking load. It can mean 8 times the heating from friction. A rope moving at 7 meters per second passes over sheaves smoothly. A rope moving at 15 meters per second starts to strike those sheaves harder. Each strike is a microscopic injury. Millions of strikes become a crack. Cracks become failure. Engineers in the 30s understood this, not through computer models, but through hard experience. They saw ropes fail on faster systems. They buried people who fell down shafts. So they chose reliability. Today, speed is a competitive advantage. A mine that lifts more ore per hour looks more efficient. A mine that shows more revenue looks more successful. Almost nobody counts the long-term replacement costs of ropes and brakes. It does not show up in a quarterly report. And that is exactly why the quiet costs keep growing in the shadows. Detroit, Michigan, 1932. An Alice Chalmers plant. A foundry man named Jan Kowalski is working on a casting for a mine hoist drum. This is his 43rd year in the trade. The casting is cooling inside a sand mold. By process, It must cool for 48 hours. The shop foreman walks up to Kowalski. The customer calls every hour. They need the drum by Monday. Kowalski looks at the casting. It will be ready on Tuesday. They threaten to cancel the order. Let them cancel. The foreman leaves. He returns an hour later. The director says, Monday. Kowalski takes off his apron and lays it on the table. Then find another foundryman. The director does not find another foundryman. The drum ships on Tuesday. That drum, installed at the Cleveland Cliffs iron operation in Michigan, serves for 44 years. Jan Kowalski dies in 1956. His drum keeps turning until 1976. This story is not an exception. In the 1930s, skilled workers could say no, not because they were protected by unions, though many were, because their mastery could not be replaced. John Kowalski knew things you do not learn from textbooks. He knew what ready metal looks like. He knew how a mold smells when it is holding the right temperature. You cannot swap that out with a fresh graduate and a rule book. So when Kowalski said no, management listened, because the machine would carry his decision for decades. Today, workers are replaced by machines. Automated lines do the job faster and cheaper. That is progress, and it is not going backward. But a machine will not say no when a boss demands the impossible. A machine will execute the program. And if the program is wrong, the casting will be wrong. Nobody notices at the moment because quality control is often sampling, not total inspection. The defect shows itself 5 years later when the drum cracks. The people who knew how to wait are leaving, and their patience leaves with them. Cleveland, Ohio, 1925. The office of Wellman Engineering. Chief Engineer Samuel Wellman is working on a hoist design for a mine in West Virginia. He is 68 years old, with 45 years in the profession behind him. He has designed dozens of mine machines. Wellman studies a young engineer's drawing. It is elegant, a lightweight frame made from thin-walled profiles. How much does this save? Wellman asks. $12,000. The young engineer answers with pride, and the weight drops by 20%. Wellman picks up a pencil and crosses out the drawing. Redo it. Standard sections. Double wall thickness. But that's excessive. Excessive is when the machine fails and people die. The young engineer redraws the frame. That hoist, installed at a consolidated coal mine in 1927, runs until 1981. 54 years. Samuel Wellman belonged to a generation that believed in surplus strength. They did not call it over-engineering. They called it common sense. The logic was simple. Calculations can be wrong. Material can hide a defect. Operating conditions can be harsher than anyone predicted. The only defense is margin. Wellman lived by a rule. Every critical element must survive 3 times the working load. His younger colleagues called it waste. His machines outlived all of them. Today, engineering calculation is a precise craft. Computer modeling can map stress at every point. Optimization cuts weight and cost. A modern engineer can design a part that runs at 95% of its ultimate strength. It is efficient, it is economical, and it also means that one unplanned condition, one surprise vibration, one overload, one bad batch, and the part fails. Not in 5 years, not in 1 year, in months. Engineers in the 30s did not have computers. They had fear. Fear that their mistake would kill people. That fear made them cautious. Modern engineers are rarely asked to carry that fear. If a part fails, it is replaced. It becomes expected wear. It becomes planned replacement. Progress, maybe. But Wellman's machines still exist in museums, like monuments to an era that did not apologize for building heavy. There is a place in New Jersey that deserves its own chapter. Trenton, the John A. Roebling Sons Company plant, the biggest steel wire rope producer in America. In the 1920s, that plant supplied rope to roughly half the mines in the country. Its founder, John Roebling, was obsessed with quality. He emigrated from Germany in 1831. He worked as an engineer on canals. He watched hemp ropes snap, and he decided to build something better. In 1842, Roebling made the first steel wire rope in America, by hand, in his own shed. Until his death in 1869, he set standards the company kept for nearly a century. Every rope was certified, every wire was inspected, every coil carried its own serial number. At the Trenton plant, 3,000 people worked. Among them was an army of quality inspectors. Their job was simple: find defects before defects found miners. A wire with a scratch went back to remelt. A coil with uneven tension went back for rework. A rope with one weak strand did not pass. An inspector named Enrique Santiago worked at the plant from 1912 to 1953. 41 years. He personally inspected more than 1 million meters of rope. His son, who also worked there, later said, "My father never signed a document without looking at the rope with his own eyes. Never." Roebling rope had a reputation. Mines paid 15 to 20% more for it. And they got rope that lasted 3 times longer. The Trenton plant closed in 1974. The official reason was competition from cheaper producers. The real reason was simpler. The market no longer wanted to pay for quality. Rope from Korea and Japan cost half as much. It lasted half as long. But mining companies no longer calculated in decades. They calculated in quarters. And a quarterly report looks cleaner when the rope is cheaper. Hancock, Michigan, 1995. A retired engineer named Richard Henderson stands in front of the Quincy mine hoist. He is 82 years old. He worked at this mine from 1936 to 1971. The hoist no longer runs. The mine is closed. Today it is a museum. Henderson reaches out and touches the drum. "I remember when they installed it," he says. "I was 23. I helped tighten the bolts." He points to the frame. "See these rivets? They drove them by hand. Every single one was checked with a hammer. If the sound was wrong, they drilled it out and drove a new one." Henderson runs his palm along the metal. This machine brought up more ore than any other hoist in the state, and it could have kept going. But the ore is gone. Someone is filming him. It is part of a Michigan Technological University project, preserving the memories of people who worked the copper mines. Henderson talks about things that never make it into textbooks, about how operators listened to the machine, about how mechanics felt wear with their fingertips, about how engineers argued for hours over the thickness of a single wall. "We did not rush," he says. "We knew our decisions would outlive us." Richard Henderson dies in 1998. He is one of the last people who still remembers what it looked like to build for a lifetime. Today, only a handful remain in America. They spend their final years in nursing homes. Their knowledge is stored on tape. Their tools sit behind glass. Their philosophy is mostly gone. But their machines, those that survived, still stand like monuments. They do not turn anymore, but they could. There is a temptation to hunt for villains, greedy corporations, lazy engineers, short-sighted managers. But the truth is more complicated. We did not forget how to build reliable machines. We decided we did not need to. In the 1960s, the American economy entered the age of mass consumption. Things stopped being rare. Things became replaceable. A car that lasts 20 years is a car nobody buys for 20 years. A hoist that runs 50 years is a hoist nobody sells for 50 years. An economy built on growth needs consumption. Consumption needs replacement. Replacement needs wear. This is not a conspiracy. It is the logic of the system. But there is another factor, less obvious and more human. We lost fear. Engineers in the 30s saw disasters. They saw ropes snap. They saw cages drop with people inside. They buried friends. That fear shaped their decisions. They built like lives depended on it. Because lives did. Modern engineers work with computers. They see numbers, not faces. They design components, not destinies. A safety factor becomes a cell in a table, not the face of a miner stepping into the cage. This is not an accusation, it is a description. We created a world where the consequences of mistakes feel abstract, where responsibility is spread so thin it becomes hard to name, where nobody is personally at fault, and where nothing is expected to last for long. The Quincy Mine hoist, the largest steam hoist in the world, stands today as a museum piece in Hancock, Michigan. Its drum, 4.5 meters in diameter, is motionless. Its rope, which once pulled thousands of tons of copper ore each day, is neatly coiled for tourists. Its brakes, which stopped a rushing mass of metal and stone, sit frozen in the locked position. But if you look closely, you see something almost unsettling. No rust blooming across the surface, no cracks spidering through the castings, no signs of collapse or decay. This machine, built in 1929, is ready to work. It is waiting for the hand of an operator who will never come. This is not nostalgia, it is a fact. And that fact asks a question we still struggle to answer. Why do we not build like this anymore? We have walked a long road in this investigation. We saw engineers who doubled safety margins, not because they could not calculate, but because they knew the cost of a miscalculation. We saw workers who refused to rush, not because they were lazy, but because they understood that time is an ingredient of quality. We saw operators who knew their machines the way you know a living thing, not because instruments did not exist, but because instruments cannot replace intuition. We saw an economy that valued longevity, not because it ignored money, but because it counted money correctly. And we watched all of it fade away. Not suddenly, not after one dramatic disaster, slowly, quietly, step by step. The safety factor dropped from 4 to 2 because modern materials are more reliable. Cooling time was cut in half because new technology allows it. Operator training was shortened from 5 years to 6 months because automation does it for them. Each step had a rational explanation. Each step saved money. Together, they created a world where nothing lasts long. This is not a tragedy. It is a choice. We chose speed over reliability, cheapness over longevity, convenience over responsibility. It is a rational choice, if you only look at the short term. But there is another view, the one engineers in the 30s used. They did not ask, how much does it cost right now? They asked, what will it cost in 50 years? They did not build for a quarterly report. They built for generations. They did not build for themselves, but for the people who would come after them. We lost that view. Not because we became less intelligent, because we became less patient. The world accelerated. Technology changes every year. Investments are expected to pay back in 5 years, or not at all. Who builds for 50 years when everything might change in 10? That is the logic of our time. And yet the Nordberg hoist in Hancock breaks that logic in plain sight. It was built in 1929. It survived the Great Depression. It survived the Second World War. It survived the Cold War. It survived the digital revolution. And it is still capable of working. Technology changed. The economy changed. People changed. But good steel stayed good steel. A sound design stayed a sound design. Careful workmanship stayed careful workmanship. Some things do not age, and some things we simply forgot. Maybe it is time to remember. Not because the past was perfect, it was not. Not because progress is the enemy, it is not. But because among everything we gained, we also lost something important. Patience, respect for material, fear of consequences, pride in work that outlives you. The Nordberg hoist stands in Hancock like a silent question, not aimed at engineers. They know the answer. Not aimed at economists. They have their spreadsheets. Aimed at all of us. Do we want to live in a world of disposable things? Are we willing to pay for what lasts? Are we capable of building for a lifetime again? The Nordberg drum is waiting. It is not in a hurry. It has time.